Okay, everyone, welcome to the 12th ECS and Cloud Feedback Virtual Symposium. A really great event today. We have topics covering everything from cloud feedbacks, clear sky feedbacks, aerosol forcing. Here's some housekeeping first. We have, today we have these 3 HEU style talks. We'll have some times for questions after each talk and then a short general Q&A at the end. If you have any questions or comments, just type them into the chat at any time. Then we'll come to you after the talk. If you would prefer to ask questions live, just raise your hand and then we'll unmute you. This is our executive committee. If you have any ideas for talks that you'd like to give or just any thoughts or comments on the symposium, please reach out to us. You can find our contact information, videos of past talks, mailing list sign up, and a lot more at our website, which is shown here. And I think that's the information. Our first speaker today is ECS Symposium's own Cristi Proistosescu, the assistant professor at University of Illinois Urbana-Champaign. And he's going to be talking about whether climate models can simulate observed warming patterns. So, Cristi, give you over the screen.
Okay, let's see if this works. Okay, can everybody see this?
Yes.
Yeah, looks good.
Awesome. Hi, everybody. I'm Cristi Proistosescu. I'm an assistant professor and I lead the Climate Dynamics and Data Science group at the University of Illinois. And today I'm going to talk to you about how coupled models fail to simulate observed warming patterns and how that biases cloud feedbacks. So let's look at these warming patterns. On the left, we're going to look at the AMIP interval, 1979 to 2014, because we have good observational coverage and because it's spanned by all AMIP simulations. On the left, we have SST trends, normalized SST trends from NOAA ERSST, and on the right, we have the CMIP6 historical coupled climate model ensemble. We're going to focus on the tropical Pacific, and in particular on how observations show more rapid warming in the West Pacific compared to the coupled models and cooling in the East Pacific, whereas the coupled models tend to have a pretty uniform warming pattern. To get us situated, we're going to do a quick review of tropical climate dynamics. So this is a map of climatological SSTs in the tropical Pacific. And we're going to be looking at a vertical transect going from the warm West Pacific warm pool into the colder East Pacific subtropics. So we're going to look at a vertical transect here. So as we know, this SST gradient leads to a circulation pattern with deep convection and precipitation over the warm SSTs. And a Walker circulation that leads to subsidence and no precipitation over the cold SSTs. The vertical temperature profile in the West Pacific is generally fairly close to a moist adiabat set by the sea surface temperatures. And through the weak temperature gradient approximation, we know that the free tropospheric temperature almost everywhere in the tropics is basically set by the warm pool SSTs. Over the cold SSTs in the East Pacific, though, the temperature in the boundary layer is set by the regional cold SSTs, so we end up with an inversion being set up at the top of these boundary layers. We can quantify the strength of this inversion using something called estimated inversion strength, or EIS, and indeed we see that EIS is largest in the subsidence regions over the cold SSTs. This strong inversion leads to cloudiness. So if you look at low cloud cover, we find that low clouds tend to want to live in these regions of strong inversion, subsidence over the cold Pacific SSTs. So this is going to be our view of the tropical climate circulation I think in his 2005 paper, Bjorn calls this a parochial view of the tropical circulation, but I think it suffices to illustrate our points. So what we're really interested in isn't the climatology, but the response. So we're interested in the cloud response, particularly the low cloud feedback to these warming patterns. And we're going to focus first on this pronounced warming in the West Pacific warm pool. So let's see what happens. Right, if we increase the sea surface temperatures in the warm pool, we get a fairly large circulation response. The moist adiabat shifts to follow the increase in SSTs due to the weak temperature gradient. The free tropospheric temperature everywhere increases. Consequently, the inversion strength increases. Consequently, you get more low clouds and more reflected shortwave radiation. So we should expect a fairly strong negative cloud feedback in response to this warm pool warming. If we look now at what happens with the cooling in the East Pacific in the observations, we actually get a similar response, right? So if the temperatures in the East Pacific cool, that also leads to a circulation response, further strengthening the Walker circulation, further strengthening the inversion, leading to even more cloudiness and an even stronger negative shortwave feedback. So this is our schematic view for how this observed warming pattern with more warming in the West Pacific and cooling in the East Pacific, what that should do to the cloud feedback. So we expect a stronger tropical circulation, a stronger inversion, and consequently a negative cloud feedback, much more so than in the observations, where neither is the warm pool warming as much, nor are the East Pacific subtropics cooling at all. Now, one critique of this is we're comparing a single realization of historical climate with the model ensemble, and instead we should consider ensemble variability. So we should ask the questions, do any model runs matched the observational record? So we did that. We looked at 58 climate models, CMIP6 climate models, a total of 538 initial condition simulations. And let's see what we find across the whole ensemble. Right, let's first look at this warming pattern, and in particular, one metric that both Fuglistaller and Dong et al. Showed is particularly important is the ratio of warm pool warming to average tropical warming. So if we plot this ratio of warm pool warming to average tropical warming trends over 1979, what we find is that the observations, in the observations, the warm pool warms very fast relative to the tropics, almost 50% faster. And not a single coupled model captures this relative speed of warm pool warming. Rob Wills has a paper in PREP where we look more carefully at these SST patterns. What I'm interested here is more the circulation and cloud response. So let's see what implications this has. Right, we said that one expected implication is that this should lead to a strengthening of the Walker circulation. So we can look at sea level pressure as a proxy for Walker circulation in reanalysis, in AMIP simulations, where the atmospheric models match reanalysis if forced with the right SST patterns, and in coupled models. And we can look at an index of the Walker circulation as the difference in sea level pressure between these two boxes. And we find a similar pattern where reanalysis is in this olive bar, large strengthening of the Walker circulation. AMIP is centered around reanalysis, but not a single AMIP not a single coupled simulation out of 500 members is able to reproduce the full strengthening of the Walker circulation. The other metric of atmospheric response is inversion strength. So if we look now at trends in EIS, again, in reanalysis, in AMIP models, which match reanalysis because they're forced with the right SST pattern, and in coupled models, and we focus on the average EIS trends over the stratocumulus regions, we find a similar story where this time there's a couple. This time there's a couple of coupled simulations that can reproduce the trends in EIS, but by and large, there's still this big bias where overall very few coupled simulations can really reproduce these trends in EIS. Okay, and now on to really what we're most interested in, which is the cloud radiative response. We can only diagnose the cloud feedback in 9 models for which we have radiative forcing diagnosed. But in these 9 AMIP simulations, when forced with observed SSTs, we indeed find a very negative radiative response associated with a low cloud increase in the East Pacific. And we don't see that in the coupled simulation, at least in the ensemble mean. But not only in the ensemble mean, we can look at individual ensemble runs. So in these 9 models, we can compare the radiative feedback over the AMIP interval in AMIP simulations in olive, and we find a very negative cloud radiative feedback. Sorry, this is the net radiative feedback. We find the very negative net radiative feedback, much more so than in any of the coupled simulations in the orange histogram, and also much more negative than the equilibrium feedback associated with the long-term climate sensitivity. So the same story holds where not a single coupled climate simulation is able to reproduce as negative of a radiative feedback as the AMIP simulations. And I hope I've convinced you that that is because they can't reproduce the right SST pattern. Why can't they reproduce the right SST pattern? Well, the cloud feedback community.
Cristi, yeah, I think your slides have stopped advancing. I still see the maps, the radiated, the CMIP 6. Let's see, maybe exit slideshow mode, or stop sharing. Okay. Share your screen.
Oh, let's try again. This has never happened before. Okay, is this where you got stuck?
Hold on, it's still.
Yeah, it's buffering.
It still says has. Yeah, that was the last slide I saw.
Okay. I'm sorry, my internet should be pretty good. Can you see it now full screen?
Yeah, it didn't look like an internet problem. It looked like it's probably a Zoom / PowerPoint. Yeah, we can see it. It is going really slow. It is.
Is it advancing now?
It is really slowly brightening on my screen.
Yeah, we're not seeing the histograms, Cristi. Okay, there we go.
Now we see it. Yeah, there they are.
I'm sorry. Okay, let's keep going then. Okay, so what I was talking about here is that if you look at histograms in each of the simulations with the AMIP simulations in the olive bars and the coupled ensemble members in the orange histogram, we find the same story. Not a single coupled simulation can reproduce as negative of a cloud feedback as the AMIP simulations. And I hope I've convinced you that this is because it can't reproduce the SST pattern and the attendant atmospheric circulation response. What are some of the proposed mechanisms? Can you see the list of mechanisms now?
Yeah, that looks good.
Okay, so we haven't thought much about it, but different communities have. And I was able to find at least 10 proposed mechanisms for why coupled models tend to not be able to reproduce specific SST patterns. I don't know which one of these is true. My own preference is to say that it's probably an underestimation of low frequency internal variability, but I think it's very much still an open question. This, I think, has strong implications that our community should think more about, in particular because our constraints on cloud feedback tend to focus on the cloud response to meteorology as summarized in cloud controlling factors, or the cloud response to SST patterns as summarized in Green's functions. But generally, all projections and estimates of ECS tend to rely on coupled modeled patterns or emergent constraints based on coupled models. And the one interval where we can really test these coupled model patterns, they fail. Maybe there's one model that comes close, but is it more likely that we really live in a 1 in a 500-year event, or is it more likely that our coupled models are biased? I think it's more likely that our coupled models are biased. This is kind of where I'm at. I don't have a lot of answers. I mostly want to spread around my confusion to everybody, hoping that somebody is going to be able to come up with an explanation. The one thing I will say is that if we look at the Pliocene, for example, as an estimate of what the long-term SST patterns are, the Pliocene is not really our friend. There's big uncertainties in these paleo patterns, but at least some of these reconstructions show that it's possible that this pattern is going to switch to a much stronger East Pacific warming on long time scale compared to coupled simulations, which should lead to a very strong feedback. Conversely, if the pattern holds, we might have a lower climate sensitivity, or at least a lower transient response. I had a slight emergent constraint, but given the technical issues, I'm not going to show it. So in conclusion, the observations show that Whirlpool SSTs have warmed very fast. Coupled models fail to reproduce this pattern, even accounting for large ensemble. And then this Whirlpool warming leads to a strong warming of the free troposphere, a Walker's cell acceleration, a strengthening inversion, and increased cloudiness. All of this leading to observed SST patterns driving much more negative radiative feedbacks compared to what coupled models can generate. That's what I have. I hope I've confused you enough to get you interested.
Awesome. Thanks so much, Cristi. There's some interesting discussion in the chat.
Can I ask a question, Nick?
Yeah, sorry. Is it a clarification? I just want to summarize the chat quickly.
Okay, yeah, go ahead.
Yeah, so Gavin Schmidt points out that it might be worth noting that if you look at the extended period from 1979 to 2020, the observed patterns look a lot more like the model patterns.
So I have, and these are the patterns extended to 2020. And the North Pacific discrepancies has decreased because of the blob, but the subtropical Southeast Pacific and the Southern Ocean are still discrepant. And if you look at the feedbacks, now you start having a couple more ensemble members that can reproduce the full pattern, but there's still overall a big discrepancy. And actually this flip suggests to me that it's probably internal variability. And of course, if you look over enough enough positive and negative phases of internal variability, the trends aren't going to be discrepant, but it does seem like the maximum deviations in the coupled models aren't large enough.
Okay, Andy, do you want to ask your question?
Yeah, I was going to ask Cristi, for long-term global warming, what you really care about is whether the models can get the long-term pattern right. And that I think seems different than whether it can get sort of this kind of short-term variability right. Do you think that the inability to get the short-term pattern right suggests that the models might not be getting the long-term pattern right, or what's the relationship between those?
It really depends on what's the mechanism. If it is internal variability, then it shouldn't directly matter, although high internal variability can suggest stronger feedbacks. If it is some of these other mechanisms suggested, like the fact that the models don't capture the nonlinear ENSO response, or the relation between wind stress and undercurrent isn't right in models, maybe because there's not enough vertical resolution, then that can bias the coupled response in the tropical Pacific. So I think it really depends on what the mechanism is. If it's the Southern Ocean, then maybe it won't matter on really very long equilibrium time scale, but it might still matter on multi-decadal, on fairly long transient time scale. So I think it really depends on what the what the mechanism turns out to be.
Okay, thanks for that. There's a lot more going on in the chat, which I'd encourage everyone to check out, but I think we should move on to our next speaker.
Yep.
Okay, sounds good. Thanks, folks. Our next speaker is Lea Albright, a PhD student at the Sorbonne and at the Max Planck Institute, where she's working with Sandrine Bonny and with Bjorn Stevens. And she'll be talking today about the lower bound on anthropogenic aerosol radiative forcing. So, Anna, when you're ready, you can share your screen.
Yes. Yeah, thanks for the introduction. Today I'll be talking about some work done together with Cristi, as well as Peter Hybers, titled Origins of a Relatively Tight Lower Bound on Aerosol Forcing from Bayesian Analysis of Historical Observations. And this work began as a critique of the Stevens 2015 aerosol study during my time as an undergrad working with Peter and Cristi. But then, as you were saying, I started a PhD with Bjorn, and in parallel, this work has grown somewhat in scope. So today I'm in the somewhat unusual position of presenting right before my advisor and talking about a project that started to reevaluate his work. Aerosol forcing is a persistent source of uncertainty in Earth's energy budget. And as seen in the schematic, the uncertainty is still large in AR6. There are two sources of constraints on this lower bound, or on aerosol forcing. The first is from process-based constraints, but these approaches can only constrain the upper bound, whereas the lower bound, or how negative aerosol forcing can be, is instead constrained by empirical or top-down methods. Within these top-down methods, values tend to cluster around either -1 or -2 watt per meter squared. And what we're interested in is understanding why similar frameworks yield considerably different bounds, even though they use similar forward models and similar sampling techniques. I'll first present our flexible Bayesian model formulation. For the temperature response to radiative forcing, we use the emulator of Proistosescu and Hybers. And this linear response function has 3 timescales, and critically a different radiative feedback for each timescale. And physically, it's equivalent to the emulator used in AR6 to constrain future projections. For the Bayesian likelihood, we assume that the difference between forced and observed temperatures can be modeled as a multivariate Gaussian with a covariance matrix sigma. And this covariance matrix comprises correlated internal variability with an AR1 coefficient rho and variance estimated from the CMIP6 ensemble, as well as uncorrelated observational error, which we take from HADCRU. Following Stevens 2015, we model aerosol forcing as a log linear function of global aerosol precursor emissions, but we include not only sulfur dioxide, but also black carbon and organic carbon. The term here on the left in red represents aerosol radiation interactions, and the term on the right is aerosol cloud interactions and is assumed to saturate. I'd also say that we have broad uniform priors on all the aerosol parameters in order to avoid circular reasoning. And we have separate scaling parameters to account for uncertainty in volcanic forcing and non-aerosol, non-volcanic forcing. So this simple model permits for more detail than previous studies that have simply rescaled AR4 or AR5 forcing, but it's still a highly simplified model. And so to test its skill, we fit it to 10 simulations from CMIP6. And as you can see in this figure, the simple model does a very good job at emulating the response of the more complex models. And so in other words, the parametric uncertainty in the simple model can span the full range of structural uncertainty in the GCMs. And we also see that representing or using global emissions seems to be sufficient for representing global aerosol forcing. Putting this together, we get a best estimate of present-day aerosol forcing of -0.85 and a 5th percentile lower bound of -1.3, as seen here or noted by the blue line. And conceptually, how the Bayesian framework works is we solve for a joint posterior distribution of parameters that yield model temperatures with the mean here in black, that are most similar to observations in red. So now a critical listener might say, okay, here's yet another aerosol forcing lower bound in the literature. But what we're really interested in is understanding why every study seems to get a different bound. And we think we can explain or reconcile foregoing estimates using 3 assumptions. First, the time interval used, also assumptions about internal variability and observational error, and whether or not studies use ocean heat uptake or not. Using pre-1950 temperatures, Stevens 2015 gets a very tight lower bound of -1.3. And if we make similar assumptions, we can get a similarly tight bound. But if we account for non-greenhouse gas forcing, uncertainty in temperatures, and a potentially more linear response, we instead get a lower bound of -2. This exercise is useful because it gives us some insight into what is bounding aerosol forcing. Here on the left, we can see what happens when we project our model forward to out of sample temperatures after 1950. And in essence, we see that there's too much cooling followed by too much warming in almost the entirety of the distribution. And on the right are 2 time series SO2 in blue, and then essentially greenhouse gas forcing, but non-aerosol, non-volcanic forcing in red. And first, rather obviously, these 2 curves have different structures. And so up until a certain point, say about 1980, a strong or very negative aerosol forcing can be masked or compensated by a high climate sensitivity. But then after SO2 peaks and declines, that unmasks this would unmask a high climate sensitivity and lead to excessive warming relative to observations similar to arguments given in previous work. And from this, we infer that the richer temporal structure after 1950 results in a reduced capacity for aerosol forcing and climate sensitivity to simply trade off in explaining observed temperature trends. And indeed, there's a modest anti-correlation between aerosol forcing and ECS using pre-1950 temperatures that goes to 0 if we use the full record. Other studies that have gotten a bound around -2 using the full record appear to get there on account of using or having more persistent internal variability. And indeed, if we increase internal variability 5-fold, mostly by increasing its persistence and also add large and correlated errors in observations, we can get a lower bound of -1.8, mostly in line with these estimates. And there's, as Cristi was saying, open questions about how much low frequency internal variability there is, and whether or not coupled models capture it. But here I'd just say that we really have to strongly degrade certainty on temperatures if we want to push our lower bound towards -2. One other thing that previous studies fit to is ocean heat content. And in our framework, we can calculate the top of the atmosphere radiative imbalance as the difference between the net forcing and the radiative response to forcing. And we calculate this using our posterior distribution and then median radiative feedback parameters from CMIP5. And when we do this, we find this figure, we get this figure on the left, where our model predicts too large a radiative imbalance compared to observations here in blue. And one way to get these two to match is by decreasing net forcing, by having more negative aerosol forcing. But another way to reconcile the two is by increasing the radiative damping. And so as a heuristic example, we change the feedbacks. Instead of being from coupled models, we make them match the AMIP simulations. And then we get this figure on the right where the offset is much less noticeable. And we call this offset or this difference a sort of ghost forcing, which inversions can either attribute to a need for more negative FNet, more negative net forcing, or rather to a need for stronger radiative damping. And previous inversions that have used ocean heat content had priors on radiative feedbacks that were informed by coupled models. And as expected, they then got more negative aerosol forcing. But what we're saying is that right now, there just needs to be more certainty about these time-dependent radiative feedbacks before ocean heat content can reliably provide additional constraints on aerosol forcing. And just before concluding, I wanted to note that Smith et al. Have a very nice study that came out recently, and they obtain a lower bound of -1.6. And we can explain the offset, -0.3 offset with our study using two assumptions. The first, they use ocean heat uptake as discussed just now. But in their estimate, if they only use surface temperatures, their lower bound is instead less negative, -1.4. And we use time resolved observational error. But if we use their time mean value, we get a lower bound of -1.4, reconciling the two estimates. So to wrap up, we, based on our Bayesian analysis of historical temperatures, we find a most likely aerosol value of -0.85 for present day and a lower bound of -1.3. And three recognitions enabled this relatively tight constraint. First, that a simple aerosol model skillfully emulates aerosol forcing from more complex GCMs. Second, that aerosol forcing is relatively insensitive to volcanic forcing, which I didn't discuss for the sake of time. And third, aerosol forcing and climate sensitivity cannot simply trade off when using the full temperature record. That said, there are still two primary caveats. First, if internal variability is larger than CMIP6 controls and observational error is larger than HADCRU, then the lower bound gets pushed towards -2. And right now, I'd say it's too early to rule these two out based on paleo evidence and also work on correlated errors in observations by Duo Chen and others. And second, previous estimates based on ocean heat uptake would suggest more negative aerosol forcing, but there's still uncertainties about the trade-offs between these time-dependent radiative feedbacks and radiative forcing. And so kind of in a nutshell, our best or baseline estimate is -1.3 for the lower bound, but there's still kind of a beast lurking in the water when it comes to uncertainties about low frequency temperature variability and the use of ocean heat uptake. Thanks.
Yeah, fantastic. Thanks, Lea. That was a great talk. I see already there's a question in the chat from Kyle Armour. He asks, he says, I think the Zana et al. 2019 ocean heat uptake estimate is biased low in recent decades.
Okay.
Did you try other, i.e. in situ estimates, and how does this affect your results?
Yeah, it's a really good question. We didn't use other ocean heat content estimates because I think in future work, it would be useful to have this be the focus. This was just kind of a heuristic example of another way that we could conceivably get more negative aerosol forcing. But yeah, I think in future work, it would be useful to compare different ocean heat content estimates. And ideally to have, because to go back to this slide, Zana et al. Estimate is also based on infilling SSTs into the ocean interior. So we also see a bias probably due to errors in SSTs in the 1940s. And so I guess ideally to have an estimate of SSTs that's independent of the surface temperature constraints that we're already using to not double call or double count these. So just an independent estimate, and to do this inversion again in a more formal way instead of kind of this heuristic example where we just change the feedbacks.
Great, thanks. Nick Lewis points out that in situ ocean heat uptake observations don't go back to 1850.
Or it was to 1870.
Yeah.
And yeah, so just taking the Zana et al. Estimate to 1870 and assuming equilibrium in 1870.
Great, so we have plenty of time for questions. If anyone. Thorsten put a question in the chat. I'm not quite sure what he said. Could one constrain on long-term change and pick numbers from AR6? Maybe Thorsten, could you elaborate on that? Like which numbers you have in mind?
Hi, can you hear me? I just meant for the ocean heat uptake. Is it possible you don't need this time series, just, endpoints? Is that enough for you to constrain on?
Yeah, I guess in principle, you could, if you had a certain number of points as kind of a lookup table and interpolating in between, given that there is a lot of high frequency or a lot of variability in this estimate of the radiative imbalance,
Yeah, this would be like 20-year averages or something like that.
I see. Yeah. No, I mean, that would be a way to circumvent.
Yeah. Yeah, I mean, I agree with Kyle. This looks really low for the 2000s, sort of. The last 20 years, this is a really low number. Yeah. Actually, your model seems better.
Yeah, I think compared to, it's also maybe a bit hard to see on the scale. Compared to the Sherwood estimate of the radiative imbalance, this was a bit too high by about maybe 0.2 or 0.3 watt per meter squared. And this mean over the recent period was in better agreement with the Sherwood et al. 2020. But yeah, it's good to know that this in general is the Zahn et al. Seems to be biased a bit low.
Just maybe a question for the audience, but Bjorn asks what the AR6 best estimate was for aerosol forcing. Is it the same as the Smith et al.?
I took it here. Yeah, I think it was a bit more negative than 1, maybe minus 1.2, but there are certainly people who are better equipped to answer this than I am. Yeah, I just made the schematic based on, yeah, there were different bounds given, but I think this was the one that synthesized different lines of constraint. So the median, I guess, or the mean is quite similar to our baseline estimate.
Okay.
So can I just interject for a second?
Go ahead,
so I
Cristi.
think Anna Lea, I don't think really understood Torsten's question, but I think she actually answered it, which is by the Sherwood et al. Estimate for the net imbalance in present day is still much more consistent with the AMIP if we run it with the AMIP feedbacks than the CMIP feedbacks. So it still suggests that running this inversion with priors and feedbacks from the coupled models is gonna drag the radiative forcing towards more negative values as it tries to match the end points.
Right. Is there still time if you want to have more discussion? Or there's a question from Ursula who asks, I'm curious about aerosol forcing being relatively insensitive to volcanic eruptions. Could you give us a preview of what you meant by that?
Yeah, so I guess what we find is, for instance, conditioning on the 5th percentile of aerosol forcing in our distribution, then the distribution of the volcanic scaling is the same as not conditioning on the 5th percentile. And there's also no correlation between how much we have to scale volcanic forcing and what the aerosol forcing is. And so from that, it's a bit surprising. So we thought that seems to suggest that it's less essential to kind of sub-select periods of quiescent volcanism in order to disentangle the two, because I guess one could think they're both negative forcings, that they would have some sort of compensation, but we're finding, at least when we integrate all the terms into this Bayesian framework, they don't seem to trade off. But we do find, consistent with previous studies, that there is some sort of, we have a reduced efficacy of volcanic forcing, about 0.7, but then there's other studies that also say over the 20th century, volcanic forcing, and so were co-occurring, so to perhaps take that reduced efficacy with a grain of salt. But yeah, I guess to answer the question, we just don't find a relationship between aerosol forcing and volcanic scaling in our framework.
Great, thanks. Let me ask one last question before we move on to Bjorn, which is that since you have a sort of Bayesian framework, presumably you can incorporate other pieces of evidence. And I thought one of the great parts of Bjorn's paper was how he, kind of weaved together a story using different pieces of, or sort of different lines of argument. So I wondered if you thought about like incorporating what we know about the interhemispheric warming differences into this framework to kind of see how consistent that is with your emulator approach.
Right. No, it's a really good question. It's something that we did think about because of course that makes use of more information. But then we also thought that given there's still a lot of uncertainties in kind of interhemisphere cross-equatorial heat transport, and if you use these box models, they also don't allow for, you'll have different feedbacks in each hemisphere, but it doesn't take into account kind of the east-west gradient, which Cristi was talking about, which seems to be so important for differences in feedbacks. And so at this point, I mean, maybe in future work, that could be something, as you say, makes use of more information. But right now, it just seemed the uncertainties were too large, kind of outweighed the benefit of having more information. But yeah, I think the Bayesian framework is certainly amenable to kind of, as Bjorn in the 2016 paper on ECS, this kind of storyline approach, which kind of inspired our paper as well, to think of these physical storylines and how to quantify them.
Great, thanks so much. And thanks for a great talk.
Thanks.
I think we should move on now.
Okay,
Jonah?
for our final talk of the day, we have Bjorn Stevens, Managing Director of the Max Planck Institute for Meteorology. And he's going to be talking to us about what we know about clear skies.
Sorry about that. I forgot to unmute. So let me share my screen again here. But so you saw the first slide. Can you hear me?
Yes,
Yeah, we
yes,
can hear you. We
can.
see your slides.
Yeah, and you see Gert-Jan van Oldenburg?
Yep, we see that.
Yes.
Yeah, so I just thought it's maybe take a moment. He passed away. And so that was sad news, but we also had some good news. So not just in memorandum, but we can also be in awe of Suki and Klaus for their great achievement of putting our science on the map. So I wanted to make those two comments, and one more before I start, which is that the work I'm going to present has really been a fun adventure with a lot of young people coming to our institute who are pointed out here, Joao Bao and Stella Bourdin, Sally Lacey, and Lucas Kluft. Particularly Lucas, I've done a lot of this work with together. I also mentioned some people at the bottom. Their papers have been really influential to how I think about some of these topics. So what do we know about clear skies? The idea here is that that clouds, there's a good argument that clouds actually don't matter for climate sensitivity. And if you're interested, you can ask me later. And so going on that premise, we can say, well, what do we know about clear skies? So the way we're going to go about this is this normal wiring diagram approach, where we break the puzzle into two big pieces, forcing and feedback. And the forcing we break into many more pieces, that, you know, the stuff that depends on tropospheric temperature, stratospheric adjustment, instantaneous forcing, you know, surface adjustment clouds. And we play the same game with feedbacks. The important thing when you look at it here is that if you think of this as a state dependence problem, so if S is climate sensitivity, in the energy balance models, often we think of S as depending on T, and so we talk about T state dependence, and we hide a couple other parameters away, and we're going to look at those. So those other things are relative humidity, effectively lapse rates measured by an entrainment parameter, surface albedo, which we won't talk about, and CO2 itself. So you can have state dependence from all of those guys. And that's what we're going to look at. We're going to do it a bit differently than normal. So the reference is what people normally do is they take GCMs, and then you have this big mess of errors and physics. And you're trying to figure out how it works by being really clever in the analysis. And so in many of the talks you've seen the ways in which people are very clever to extract the different pieces of the feedback or the forcing. So we'll go back to an old-fashioned way. Jim Anson did this a long time ago, but using RCE as an interpretive framework. The nice thing about RCE is that we can get rid of clouds. We don't have to sort of analyze them away, but we can run RCE in clear skies. So the clouds kind of go away from us, and it's conceptually clearer. And it avoids sort of hidden cloud masking effects. So that's nice. So the first thing we can look at is forcing. And already we get our first surprise from RCE. So when we look at forcing from AR5, we had 3.7. That was the Jessica Vial's number. And in AR6 in the WCRP, the Sherwood Webb et al. Report, That got bumped up by a couple tenths because of cloud adjustments. And so you'd expect RCE with no clouds and hence no cloud adjustments to be less than AR5, less than 3.7. And lo and behold, we get 4.7, a big number, which we struggled to understand, but then we did. And it's mostly due to the lack of cloud masking. So clouds mask some of the forcing. And we use the Manabe humidity profile, which Manabe weather humidity profile, which is pretty darn dry. And the humidity also masks the forcing. So that gave us the extra watt. So so there we get a hint that humidity matters. And so when Stella came and visited us, we looked at that. But before we did that, I want to give you a little bit some of the feedback numbers. So for the feedback, here's the Sherwood-Webb et al. Numbers, Planck 3.2, lapse rate water vapor 1.15, net -2. RCE, we end up with the same net, but we get there in a very different way. So we have, in this dry Manabe atmosphere, we have a much bigger Planck effect, and that's again this water vapor masking, and we have a much larger in magnitude lapse rate and water vapor. The fact that we land in the same place is mostly coincidental, but mostly coincidental because you can vary the combination of those two by changing the relative humidity or changing the lapse rate or changing the temperature. So as I started to say, Stella, when she was here as a master's intern, looked at that and wrote a nice paper in GRL where she said, let's just look at this humidity, relative humidity state dependence. And so she fixed temperature in RCE, and the diagram on the left here you see is just for a fixed temperature, and you just vary relative humidity in the base state. So it's always a constant relative humidity experiment, but you start, hello? Okay, so it's always a fixed relative humidity experiment, but you start with different base state relative humidities. And you see the scale here of climate sensitivity goes over a huge range, and the relative humidity goes over a huge range, but it increases quite markedly. And once you get into, we're at warm temperatures in this fixed temperature, once we get into this sort of window closing regime, it increases a lot, particularly for a moist adiabat, which can pack a lot of water vapor into the lower atmosphere. So Stella found a clever way of asking then, what is it about the humidity profile that matters? So she came up with this little C-shaped profile, and she said, well, with this profile, we can shift it, we can change the mid values, we can change the top values, we can change the low values, and we can fit the profile to pretty much any model and see how much it matters. And what you find is that the mid-tropospheric humidity actually matters quite a lot. So does the upper. That was less of a surprise. And when you fit to things like AMIP models, what you find is that the AMIP models have a maybe 10 to 15% spread in clear sky sensitivity, just implied by their relative humidity changes, which aren't very big. But if you let the models loose and do things like RCEMIP, you see because of convective aggregation, we can get huge differences of humidities, which have huge effects on the clear sky feedback. So that's relative humidity. One of the things you might have noticed in that last diagram was we did this, for two lapse rates, a uniform and a moist adiabatic lapse rate. And there's no surprise. We all know that the lapse rate affects the climate sensitivity. But Zhuawei Bao, postdoc here, came up with a clever way to do a multi-plume parameterization with entrainment in the RCE model. And what he showed was here, this diagram shows the deviation from the saturated isentrope here, 0 of temperature with pressure. And all the gray lines are different CMIP models. And then his little entraining plume model can more or less span the CMIP range. So we can look at the effect of the lapse rate and how much it varies among CMIP models by varying his entrainment parameter. And what you see is a small effect of entrainment. Again, kind of like the tropospheric adjustment, 0.1 to 0.2, 0.15, as you sort of span the range of the CMIP models. Here we use Stella's relative humidity profile, which is fixed to temperature. And on the right, we just vary CO2. And then for the different lapse rates, from a fixed lapse rate where you get a big sensitivity to a pure moist adiabat where you get a small one. And then you sort of span the range of the CMIP models, showing how you can calculate the effect of the lapse rate biases in clear sky sensitivity. Temperature, of course, matters. That's what people have looked at a lot. And we were curious if you held everything else fixed, just relative humidity, and came back to some of the stuff that Catherine Marana and Torsten did when they were here, which is look at how if you just vary temperature, how the climate sensitivity varies. And the gray curve here shows varying surface temperature versus climate sensitivity for fixed CO2 and fixed relative humidity. In the past, we had gotten curves like this where you see a real increase in sensitivity, looking like you're getting ready to run away as you get into the closed window. We redo this with line-by-line calculations, and we see that it's much flatter. So you do get some state dependence. And then it saturates here when the window closes. And that saturation, we understand it's really just CO2 stabilizing the climate, which is it's a funny thing, right? Because the CO2, when you're in a closed window situation, on the one hand, it is your source of forcing as you increase CO2, but it's also your main source of feedback. And I'll come to that in a second. So by now you're probably lost. It's a bit of a zoo. You know, we expanded the state space of clear sky sensitivity. And we looked at relative humidity, we looked at temperature, we looked at lapse rate, and they all kind of matter. The advantages in this framework is that we don't need to confound biases with signals. We kind of know what those values should be. We haven't worked that through yet, but if you just take a sort of morning guess at it, which I did, and put all the numbers together, what you find is that the climate sensitivity using these feedbacks of a clear sky is about 2.9 plus or minus 0.6 Kelvin. So this is for clear sky. I think we could do a much better job on that. I bet if we integrated over the observed state, given how well we know it, we probably could cut this down by a factor of 2. The uncertainty. So I think there's a chance to get a pretty good estimate of clear sky sensitivity. So this shows how things behave. You could try to remember those, but in doing this work, we kind of kept going back to radiative transfer and tried to think what's the conceptual model for understanding this. And I'll try to explain that now. Radiative transfer experts, this might be old hat, but it was new for us. And the way we found it most useful to think about these things is in the temperature of the optical depth equals 1 line in the atmosphere. So if we look at the atmosphere on the upper right here from space, this is an image in the 6.3 micron line, which is over here in wave number space at about 1600. It's a water vapor line. We don't see very deep into the atmosphere because we get about halfway through the atmosphere, not even. And the atmosphere is opaque because of water vapor. As we reduce the energy of the photons and move to smaller wave numbers here, what we do is we move out of the low vibrational bands and we come into this range here where the atmosphere has to be so water vapor rich, it has to be so warm that the continuum effects start making the atmosphere optically thick. So it's optically thick at very warm temperatures only if we had an infinitely deep water vapor atmosphere. And then over here for these low energy photons, the rotational bands mean that we don't need much water vapor before we're optically thick. So from this point of view, if we just had a water vapor atmosphere, then the emission temperature would be the integral, the average of this curve weighted by the Planck response. But of course, we don't have a water vapor atmosphere. We have CO2. Whoops. We have CO2. And CO2 acts like a giant island in this water vapor sea. What it does is it sticks out there and it's 15 micron band, and you have a little hint of these small shores of the 10 micron band. And so when we look down from above, we see the stratosphere in the center of the band, and we see the wings of the band in the troposphere. So the emission then follows the supremum of these lines, the blue and then the orange and then the blue. Of course, we don't just have water vapor and CO2, we also have the surface, and the surface tends to be warmer, cooler than the continuum temperatures. And so the atmosphere, looking down from above, you can follow the water vapor, then you go up on CO2, and then you follow the surface. And that's why we call it the window, because at that temperature, we're not warm enough to be seeing the water vapor. So we're seeing the ground, and then we see the water vapor again. So if the main thing about this, the Simpsonian fact here is that this blue line doesn't vary when we change temperature, but the orange and the brown ones do. And that's because water vapor is tied to temperature. So the optical depth is always at the same temperature of the water vapor. So the blue parts of the spectrum are sort of out of play when we talk of feedbacks. and just the brown and the orange are in play. And so if we increase CO2, it's essentially raising up this island. And so now the emission temperature goes down, and so that's a positive forcing. And this is the having a hard time, so that's a positive forcing. And if we increase the temperature, the floor goes down. So here the surface temperature goes down. We expose more of the Simpsonianness, the non-responsive part of the spectrum, which is the water vapor feedback getting stronger, that ramp up. And the CO2 line also comes down to warmer temperatures. So it goes down with, it's anchored to the surface temperature. So the window becomes smaller and the CO2 becomes more important. And eventually, as we get warmer and warmer, so the surface temperature goes below the continuum, we get this sort of saturated water vapor atmosphere. And the only thing we have left to radiate back for us is CO2. So this model will explain everything that you saw in the last slides. It's a very nice conceptual way to think about the radiative response. And I know some people in the audience have been thinking about things in this way much longer than me. So excuse me if I'm humoring you there for finally catching up with your thoughts. So that's it in a nutshell. That's on the slides. You can look at that later. But I would just say that this view, I think you can understand just about everything that we see in the model. And then I would just summarize here by saying, what do we know about clear skies? I would say we know a lot more than we make use of. And using this knowledge should help us better avoid convolving biases with uncertainties. And here I'm maybe just a little bit responding to this tendency to, I mean, I really don't understand why people find the CMIP models so interesting, because what they're really doing is they're quantifying the biases in many cases and calling it uncertainty, which it's not, because we know what the relative humidity profile is. We know what the lapse rate is. We know what the temperature profile is. So the radiative response also is pretty linear in all those sort of things. So using that knowledge, we can calculate what the clear sky is, and then all that's left for us to do is work out clouds. And there's an argument, like I said, that clouds don't matter a whole lot. Then again, and this is some of the stuff that was posted to in response to Chrissy's talk, there are big changes afoot. There's Norm's work, and there's some work we've done with George Tatsaris looking at these really huge trends in shortwave radiation that we're seeing over the last 20 years. And we're getting a better and better understanding of how convective organization sort of enters the mix in all sorts of ways that affects TU and epsilon. So with that, I'll stop. Thanks.
Thanks, Bjorn. Yeah, so we have a few minutes of questions for Bjorn, and then we'll have kind of a general discussion after the hour. I don't see anything in the chat yet. Maybe to play devil's advocate a little bit, Bjorn, I guess what I was a little confused about is in the, if you do take the CMIP models seriously, they seem to be really consistent in their estimate of the clear sky feedback. So I guess what is there, I mean, maybe we would want to understand the details of radiative transfer a little bit, but so what is there left to really gain from
yeah,
studying this?
If you look at the feedbacks, for instance, with the lapse rate in water vapor, so there's a, I don't know, a 10 or 15%, say a 15% uncertainty in the lapse rate in water vapor. And even for which you get it by cancellation, and then for the Planck. So I think we can narrow those because we know what I mean, they're not just, they're just not samples of reality. I mean, somehow people seem to think that every CMIP model is a plausible sample of the world. And what they measure when they measure the differences are really just the effect of their biases is the argument I'm making. So we could, I mean, like we showed, that's a small effect with Stella's, you can correct for the relative humidity bias. But we know if like IPSL model has a whopping relative humidity in the middle troposphere. So we know that will make the climate sensitivity seem too high in that model. But that's not uncertainty, that's just bias. So I don't know if
yeah, I guess when you add them up together, it's, I mean, there is a lot of cancellation. Nader, who I think is on this recall, has done a lot of nice work on that. So yeah,
yeah, there is. But if bias is canceled, does that make you feel better?
Well, he, maybe Nader, if you want to jump in here. But for example, there's spectral reasons to expect the lapse rate and water vapor feedback and Planck feedback to cancel.
Yeah,
I guess maybe the way I would,
Go ahead, Nader.
I'm sorry. Yeah, so I mean, we had one paper where we just we didn't do the conventional feedback analysis, and we just looked at essentially Gregory plots of the long wave clear sky radiation. And if you look at that for quadrupling experiments across HUMID-5 models, you get very consistent slopes with a very narrow range. So it does seem like chopping up feedbacks into Planck and water vapor and lapse. And a confusing thing about Planck and water vapor and lapse is that they're calculated with the climatological clouds in them. So a model's lapse rate feedback is influenced by its climatological clouds. And so there's a lot of sources of spread, which do seem kind of spurious if you're just interested in the clear skies. And the clear sky picture from the models does seem very consistent if you just directly diagnose the response of the long wave clear sky.
But probably we didn't need the models for that, did we? In a way, we kind of know. I mean, you could do it from the reanalysis. Essentially, what it's saying is the model's relative humidity, whatever it has, and whatever lapse rate it has, is probably staying about the same. And the small spread just says that is measuring the spread in the relative humidity state it has and the lapse rate state it has. I don't know if you'd agree with that, Nadia.
Yeah, no, sounds about right.
I could give the answer about clouds if you want it. So
Yeah,
the answer about cloud. Here's the answer with clouds. So the way it goes is when you look at forcing, there's two things that affect the forcing from clouds. One is cloud masking, and the other is cloud adjustments. So if you take clouds away, the masking is about 0.2 minus, and the adjustment's about 0.2. So those are gone for you. Then if you look at the high cloud feedback, the FAT feedback, Yoshimori and Lucas has in his thesis calculations with RCE, is that the FAT feedback is pretty close to zero. It's hard to tell apart from zero. And really what, again, is the compensation between the change in the emission temperature and the masking of other feedbacks. So when you do that, the latest work is showing that FAT feedback is zero. So that leaves you with a high cloud feedback according to AR6, which is minus 0.2 watts per square meter. And then if you go to Meyer's work on low clouds, he's revised down based on observations the AR6 and the Sherwood-Webb et al. Estimate of a 0.4. He's revised it down to 0.19. So you have a negative 0.2 from high cloud anvil, if we leave that there, and you have a positive 0.2 from low clouds. That's just the state of the literature. And you add those two together, and so you get zero. So on the forcing side, you have masking compensating tropospheric adjustments at zero, and on the feedback side, you have the low cloud, marine low cloud, compensated by the anvil reduction. So I end up with zero when I do that. That's the argument.
Right, but when you were talking about the long wave feedbacks, you were concerned about model biases, and here you're talking about mean results. So, I mean, I think Gavin put a question about, or made a comment about sources of uncertainty, right? Which I think is, even if the mean estimate of the cloud effect is zero, the spread is still larger than the spread of the clear sky feedbacks.
Yeah, but the thing I found beautiful about the AR6 report was, if you look at AR6, the one place where we made huge progress, the biggest progress we made in my career is this halving of the equilibrium climate sensitivity. And we did it by saying at the very outset, we won't consider the CMIP models. And to me, that's sort of remarkable. And what it shows is that we can reason about a lot of these things better than we can incorporate them all in, heavily parameterized models. And maybe if we spend more time reasoning and less time pretending that we could build all this stuff up from the bottom up in elaborate parameterizations, we'd be better off as a community and further ahead.
Yeah, that's a great I don't know if Kyle or Thorsten are still on the call. I'd love to hear their thoughts on that. Hey, Thorsten. Okay, Thorsten says he could only agree. Jonah, do you want to ask your question?
Yeah, you could have cancellation of the cloud feedback to be 0, but you could still have a situation where the cloud feedback has some degree of state dependence that could play a role, for instance, in how the sensitivity could change as warming occurs. And you know, I'm just curious if
Yeah, I'm kind of two minds here on the cloud. So on one hand, tongue in cheek, almost everything I say is tongue in cheek. I'm kind of entertaining the thought that clouds don't matter. On the other hand, I wish I was more confident in that, because if you look at the series trends, they're pretty fantastic. If you would map them into a feedback, we all think it's variability. And there's some evidence that in the Northeast Pacific, the models capture some of that signal. I mean, that's the first Lobdal paper where Kyle and Thorsten are, I think, on that paper. But you also see similar trends in the Southern Hemisphere in that same period of the same magnitude, which don't fit the argument quite as well. And we're seeing these enormous changes in cloudiness from an energy budget point of view, and we just don't really have any understanding of that. And we know we have big biases in the tropics. So the other half of me is saying that we're kind of flying a bit blind into the future. And we should have a much better idea of how we expect clouds to change, particularly in the tropics, if we want to feel comfortable about this warm world we're creating. So yeah, maybe you'll have your state dependence there. Yona, I wouldn't rule it out by any means, but it's fun to entertain the thought that maybe clouds don't matter, except to mask clear skies.
I have the figure actually from that low paper. It's the first figure in my supplementary slides. Might be fun to show.
Yeah, go for it, Cristi.
So this is so top are SST patterns and bottom are radiative feedbacks, local radiation divided by global temperature trends. Left is the AMIP interval, 1979 to 2014, what I showed. And this shows that actually, as Gavin pointed out, things have switched dramatically since 2014. And it's kind of a pity that that's where our AMIP simulations run. But Norm did cajole a bunch of us to look at this later interval. So we have a couple of simulations that spanned 2014, 2017. And as the SST pattern flips in the East Pacific, the radiative response flips. And if you look at the AMIP simulations and compare it with series, yeah, you see in series some massive cloud response, particularly in the Northeast Pacific. I think this is what Bjorn is referring to. My point here is that the AMIP simulations do kind of match this, but it also shows that it can go the other way as well. There is the potential for these coupled atmosphere-ocean patterns to lead to very large positive cloud responses.
And what you see, Cristi, there is, which is more diffuse, because in that earlier paper I mentioned, they showed that you get the Northeast Pacific. So it seems like there the models are responding in a reasonable way. The degree of trend in the northern and southern hemisphere is almost identical, but the southern hemisphere does it in a very different way. It's that band. You see a hint of that band in the models as well. So they're not out to lunch, but it's just, I wish I understood if that was a coincidence or not. The fact that the trend in the southern hemisphere is indistinguishable from the one in the northern hemisphere, although it happens in a seemingly very different way.
I don't know. I have a student who's looking at this using sort of cloud controlling feedback formalism to try to understand what's driving the northern response versus the southern response. And it does seem like there's slightly different factors, but it's a bit early to say.
Okay, this is great discussion, but it's 10 past the hour, so I think maybe we should wrap up. Tons of really great discussion today, and I think the chat will be saved and posted online, and it's definitely worth checking out if you haven't. But thanks so much to our speakers for a really awesome set of talks. And yeah, again, if you'd like to present something, please contact one of us on the organizing committee. And otherwise, stay safe, everyone.